All right, let's finish this one off and actually solve the problem this time. I wanted to add that will it precipitate form because that's kind of a common thing I've seen on AP tests. It wouldn't shock me if you saw something similar. Actually, the equilibrium problem last year was a precipitate problem. There's always an equilibrium problem on the AP test somewhere in the free response. So I would guess that whatever your equilibrium problem is this year, it might not be entirely precipitates. It could be acid-base. It could be like, an equation with gases or something like that. But last year, it was precipitate. And they had to do something kind of similar, like will it precipitate form. So I wanted to make sure we kind of threw that in there. Now we can calculate equilibrium concentrations of all ions in the solution. Sounds like a blast. Let's start with the net ionic equation. So here's my net ionic. Getting rid of the spectator ions. It was the lead plus 2 reacting with the 2 iodine ions, forming the lead iodide precipitate. And we can put phase symbols in if you want to, or you can leave them out. All right, we're going to set up an ice table. ICE. And we're going to use those initial molarities that we calculated before when we were trying to figure out if a precipitate forms. So that M1V1 equals M2V2, that wasn't a total loss. We need those molarities for our ice table, just like when we titrate. When you combine volumes, your molarities will change slightly. And we want to put that in our ice table. So the lead was 0.0167. The iodine was 0.0667. 667. And initially we don't have any of that solid, but now we confirmed that it will go forward and it will form precipitate. So we're going to react these two ions as completely as possible. So in a sense, it's kind of a limiting reactant situation. But here's what you have to be a little bit careful of. When we did a lot of that acid-base stuff, like the titrations, it was a lot of 1-to-1 ratios. This is not. This is a 1-to-2 ratio. And we're going to react according to that ratio. So I can kind of estimate, like I think my limiting reactant is still going to be this lead. If I bring this down by 0.0167, that'll go to 0. This guy is going to go down by 2 times that amount. Super common mistake. But I think if I do that, it's still in excess. Yep. 0.0333. Does that kind of make sense? Now you have to be a little bit careful of the ratio. So it's kind of back to like chapter 13 where this happened a little bit more often. In the acid-base stuff, I mean, it's often 1-to-1s. Now you got to be a little bit careful. We'll react according to that balanced equation. And then this will go up by just 1.0167. So we'll be at 0.0167. Excellent. Well, that wasn't so bad. Now here's the stinky part. At the end of this ice table, it makes it look as if there's no lead. Lead was my limiting reactant, right? Well, with these precipitates or these insoluble compounds like lead iodide, they do have a tendency to redissociate. So you form some of this lead iodide, but some of it will dissociate back into lead and iodine ions. And then those lead and iodine ions swim around in the solution. They collide. They go back to the precipitate. So you do end up with an equilibrium system where we're forming solid and we're forming ions at the same rate. So you won't have any zeros at equilibrium. So guess what we need? If you said another ice table, you are right. And kind of sad, this will be the last ice table that we do together. Unless you want to do some in class, like if you want to do some homework problems or something like that, that'd be really fun too. We need some of that lead iodide to redissociate. So I'm going to essentially kind of like write my ice table with the equation flipped, that lead iodide will redissociate. And so I will have some lead ions at equilibrium, and I will have some iodine. I might have a little bit more than what I previously expected. ICE. We'll fill this in with the concentrations we calculated above. So after I shifted it as completely as possible with the limiting reactant calculation, I was left with 0.0167. You could say like moles per liter, or M. There's the lead iodide. My lead was originally listed as 0, but it's not going to stay that way. And my iodine was 0.0333 from the previous step. So here's what happens. Some of this lead iodide will redissociate. We just don't know how much. So we will form some lead ions. And do you see where we're going with this? We're going to form some extra iodine. 2x. We got to watch the ratio in the balanced equation. If I redissociate a mole of lead iodide, I'll get 2 moles of iodine ions. So at equilibrium, this will be like 0.0167 minus x. X. Ooh, 0.0333 plus 2x. This might be like one of the craziest problems you'll do all year. I mean, this has got a lot going on, doesn't it? Well, all we have to do now is set this up and solve for x, right? That's not so bad. They gave me the K value. Originally in the problem, they gave me the KSP for the lead iodide. KSP for the lead iodide was 1.4 times 10 to the negative 8. Small. Equals. Okay, so now when I do this KSP value, I'm not going to include this guy. It's a solid. We're really just looking at these ion concentrations, so I'm not going to include this right now. Okay, so let's set this thing up. I'm going to have x for the lead, raised to the first power. And I'm going to have 0.0333 plus 2x raised to the second. Don't forget that. This looks terrible. I don't want to solve for x, but I do want to use the 5% rule just one more time. If this goes forward and we do produce a little bit of lead and a little bit extra iodine, it's not going forward by much. This K value is really small. So let's simplify our calculations by getting rid of that plus 2x. I mean, we have to leave an x in the situation, but if we're like adding x or subtracting x, we could get rid of that to simplify our calculations. So if we solve this sucker for x equals... Oh, actually, no, this isn't so bad. How about 1.26 times 10 to the negative 5th? Nice. Okay, I think we're almost done. So check it out. We do get a little lead. It's not much, but we will have a small amount of lead ion in the solution from the redissociation of that lead iodide precipitate. And we will get just a little bit more lead ion. But now watch what happens. So they want to know the concentration of all ions at equilibrium that would remain in the solution. Okay, well, here's the lead. The lead plus 2. That is x. 1.26 times 10 to the negative 5th. Small. We will have some iodine. I2. Actually, let's go iodine just minus 1. If I go plug that x value in, originally I had 0.0333 moles. I'm going to get a little more. This 0.0333, that's from it being the excess reactant. There was just excess iodine in the original solution, but we're going to get a little bit more iodine from the dissociation of the lead iodide. I mean, it's tiny. I hesitate to say it's insignificant, but it almost is. 0.03332-ish. I mean, you'd have to go out like many sig figs. 0.0333, like 52-ish molar, which you probably wouldn't do. If you were leaving this at 3 sig figs, you'd say 0.0333. Yes, I get a little bit more iodine, but if I'm sticking with proper sig figs, it is insignificant. There are 2 other ions remaining in the solution. Can you find them? Do you know what they are? Look back at this net ionic equation. We had canceled them out, but they're still in the solution. It says the equilibrium concentration of all ions in the solution. Well, the sodium and nitrate are still present. They're still in the solution, and we could calculate their molarities. Actually, we secretly kind of already did. We joined the volumes and recalculated the molarity of the lead nitrate and the sodium iodide. Well, here's the nitrate concentration. Now, this was lead nitrate, moles of lead nitrate per liter of solution. Well, for each mole of lead nitrate, I'm going to get 2 nitrate ions. So I just need to multiply that guy by 2. And that gives me the molarity of the nitrate ion. The sodium, here she is. The sodium will just be 0.0667. We can't forget those extra spectators. They are in the solution. They're not part of the reaction, but they're present. So here are the other 2. We're going to have sodium from the original solution, sodium being a spectator. That guy was just 0.0667 molar. And then the other one is the nitrate ion. This, see, what was it? Lead nitrate was 0.0167, but we want to multiply that by 2. We're going to get twice as many nitrate ions. And so all we got to do is plug that in, and I think we're almost done. Nitrate, 0.0. How about 3, 3, 4? Here they are. Here are my ions in solution. The sodium and nitrate were always there from being spectators. They were 100% soluble. So I didn't really need to do a lot of equilibrium stuff to figure out their molarities, but I did for the lead and the iodine. Yeah, we figure that there might be extra iodine because it was an excess, but we'll get just a little bit more from some of that precipitate redissociating. That's where the lead comes from. The lead was the limiting reactant, but there will be a small amount of lead ion present from that lead iodide that will dissociate just a little bit. There it is. That's the end. The very last problem in the study guide, you can skip it. It's the same thing. It's just a different equation. And there's a really good one at the end of the homework, so I'd give that one a whirl. Otherwise, this is it. So I will post a quiz, not really a quiz, it's more of like a survey. I'll post it on Edmodo, and you can take that anytime. You can take it over spring break, and it'll just kind of ask for your thoughts on watching the videos. What did you think? Did this help you, hurt you? Hopefully there were some benefits to it, and it's definitely something that I appreciate your honesty, so we can kind of like use this in the best way possible in the future.